Hey everyone, this is our second video covering the graphs of rational functions for our review for this first part, 3. Our big goal with this is to make a sketch of the graph and to be able to identify all the key features that we need, including asymptotes, holes, and our intercepts. You can check your answers. So on the quiz, you'll have access to a calculator and you can always put it in. But it's important that you're able to show the work and how you get all of those key features that you see in the calculator's graph. Notice I gave us this graphic organizer here with all the key features lined up, and we'll see how to use that. In general, though, I won't give that to you on a quiz, but it is a good place for us to start. You'd have a reference of like where all these things are coming from and how you might structure your own work when you go to do these on your own. Alright, so let's jump right in on the first problem. So this is a pretty simple example. It asks us to write it in standard and factored form. Notice we did this, or we practiced doing this on the last video. For this one though, I would say it's already in standard form. There's nothing to multiply out on top. So x plus 3 over 2x minus 1, that's pretty standard. And I could try and factor it. If I look at the top, x and 3 are actually already factored down to a linear term, so there's no need to adjust those. I could try and look for a common factor. I see this 2 out in front of x on bottom. I'm thinking maybe there's a common factor, and there's no common factor between 2 and -1, or 2x and -1. So say they're actually already factored as well. So here we don't need to do any factoring or multiplying to make it into either of these forms. Cool. So our first key feature that we've always found is our domain, and we take care to identify our domain because we know we can't divide by 0. So that's always what we're trying to avoid when we're looking at our domain. To do that, we just go to our denominator, the place where a 0 could be a problem, and say, well, we don't want the denominator, 2x minus 1, we don't want it to be equal to 0. So whatever factor you have in your denominator, here it didn't matter that we took it from standard or factored form. Typically the factored form is really easy. Take it from factored form, say our denominator cannot be 0, and then we can solve this, add, divide, plus 1, 2x equals 1, cannot equal 1, divide by 2, x cannot be equal to 1 over 2. So when we talk about our domain, we're saying what values of x can we have, and basically we're saying anything but we can't have x equal to 1/2. That would make us divide by 0. That would be a big problem. Okay. So from our domain, that excluded value is either going to become an asymptote or a hole, based on what happens. So if we can remove it, if we can remove our discontinuity, this problem, this value, this factor that gave us a divide by 0, then it becomes a hole. If we can't remove it, if it remains in our simplified form, it'll be an asymptote. So I look back at my factored form and I notice, well, I can't divide 2x minus 1 out of the top and bottom of my fraction. There's no other common factor to divide out, so I can't remove it. So that means that this will become an asymptote. X equals 1/2 is going to be a vertical asymptote. That's an x value that we can't have. So I'll just take a second to add that to my graph. I'm going to go 1, 2, 3. Just making a little sketch here. They don't have to be super precise. Some axes. Well, if that's 1, then 1/2 would be right about here. And we usually show asymptotes in our graph with a dashed line. So this would be the kind of work you need to make sure you show, even if you use the calculator to help you finalize the graph. Alright, x-intercepts. So I would go down here to x-intercepts are anywhere it touches my x-axis, and I highlighted that in yellow. And the x-axis is anywhere where our y is equal to 0, or our function is equal to 0. So to find our x-intercepts, we look for places where our function is equal to 0. That's pretty easy. I'll just take my function, x plus 3 over 2x minus 1 equal to 0. And then I just have to ask myself, well, what in my fraction would have to be 0? Or what in my fraction would have to be true to make it equal to 0? Well, our top would have to be 0. So really what I can do is just take the top of my fraction equal to 0, because that's the only thing that would make a fraction 0, and say, so x plus 3 equals 0, solve x equals minus 3. That would be my x-intercept. And that's a valid thing, that's in our domain, so I'm going to go to my x-intercept at 3 and put an x-intercept. So that kind of covers the x values, the important x values we're looking at. In the right column, we look more at our y values, or what's happening to our function, the ends. So end behavior is saying what happens at the ends, the tails. Where do they go? Do they go up? Do they go down? Do they go toward a value? That's what we'll find out. To analyze this, we take the most important terms from top and bottom, typically from our standard form. It's a lot easier to draw this from our standard form because we'll know what the biggest terms are. So I go to my standard form and I see, in the numerator, my biggest term is x. My most important, the term that will grow the most, is x. And in bottom, the most important term is 2x. Both of those grow faster than the constants. Obviously, the constants don't change. Okay? And then, we're saying, when x gets really big, this is what our function will behave like. And then I see here, whenever I have an x and an x, a common factor on top and bottom, I can divide that common factor out. Divide by x on top and bottom. And that leaves me with 1 over x. Because x over x is 1. 2x divided by x. Oops, that's wrong. X divided by x is 1. Yep. 2x divided by x, that gets rid of the x's. They divide to 1, and I'm just left with a 2. So really what we're saying is, when x gets big, our function is going to behave just like 1/2. So this is the notation we use to say that. I say when x gets big, goes toward positive infinity, our function is going to head toward 1/2. Because it doesn't matter if I plugged in a big x here, our function is behaving like 1/2. So same going to the negative direction. So if x goes to negative infinity, it doesn't matter actually what x is doing. We know that our function is going to behave like 1/2. Okay. Then that covers end behavior. This statement right here is a statement of what's happening at the ends. We know as we go really far right, the function is going to go to 1/2. As we go really far left, the function is going to go to 1/2. Typically, this means it's going to turn into a horizontal asymptote if it goes to the same value. So here that goes to the same value of 1/2. So we're going to have a horizontal asymptote of y equals 1/2. That's the one value it's approaching horizontally as we go far right and left. So I'm going to add that on my graph with a green dashed line. Okay, so now we have our asymptotes. We know where it's heading, far left and right, and we know that it can't touch the blue vertical asymptote. Okay, then we just have to do our y-intercepts. So y-intercepts, here's our y-axis over here. What's true on our y-axis is that is where our x is equal to 0. That's the line x equals 0. So I just plug x equal to 0 into my function, and I should get out any y-intercept I have. So let's do that. Plug in my x 0. I get 0 plus 3 all over 2 times 0 minus 1, which is 3 over minus 1, which is minus 3. So then on my graph, go down to minus 3 and put an intercept. It's touching our y-axis there. Okay. So now we should be ready to make a sketch. We know in general our rational functions look like they're going to approach but not touch the vertical asymptote. So I know that like this is a point. I'm going here. I know it's going to get closer, but never quite touch that vertical asymptote at 1/2. Oh. So I'm just going to sketch a line down like that. And then I know as I come up, I have to touch this x-intercept over here. And then it should approach 1/2. Darn it. Should approach 1/2 as I go farther and farther left. It's a pretty good sketch. I also would note that the denominator is an odd degree. Odd degree. And that it has an exponent of, we can imagine having a 1. So that means when we get to asymptotes, they should go in opposite directions. So I know that my function should be coming from up here. And I also know it's never going to touch my x-axis, otherwise I would have found an x-intercept over here. And I'm just going to have it come down and sort of approach the horizontal asymptote. And again, we do as much of this as we can on paper, and then you're welcome to check your answers in a graphing calculator. Okay, so let's go down here to the second example. Much of this is going to be the same process. I'm going to use all these. Need to know the standard form, the factored form, and all those other key features to construct our graph. The only thing that's a little more complex with this one is that it is not written in both standard and factored form. I'd say right now it's in standard form. That's our standard form, 2x squared plus 2x minus 24 over x cubed minus 9x. There's nothing more I can multiply out there. It's written with the biggest degree term first. But I can write this in factored form, so let's zoom in on this and look at how I might factor it. There are a lot of things to think about when factoring. I usually look at for common factors first, and I notice right away that all three terms in the numerator have at least a 2 in them in common. So I could factor out a 2 out of all those, and that would leave me with x squared plus an x, and 24 divided by 2 is 12. So I factored out a 2, and a good way to check yourself is to imagine multiplying it back through. You should get the same thing, 2x squared, 2x minus 24. Yep. So I factored out a 2 in common on top, and that's a good start. On bottom, I'm going to look for common factors as well. I notice I have 3 x's multiplied in the first term and a negative 9 times an x in the second term. And I look at that, I'm like, well, there's at least an x in common in both. There's an x here and an x here, so I could take out one x from both. If I take an x out of x cubed, that gives me x squared. If I take an x out of 9x, that gives me minus 9. Great. So now we have looked for common factors and gotten a couple factors out that way. The next thing I noticed right away is that both of these are quadratics. We have a method for factoring quadratics that works with the simple ones we've been working with. So if we have some ax squared plus bx plus c, I need things that multiply to c and add to b. That's something we learned right at the start. So if I go and factor the top, there's the 2, and then here I need numbers that multiply to make negative 12 and add up to make that's like a 1x. Right? That's like a 1x. So something times something gives me negative 12, and then something plus something, or those two things added, should give me 1. Well, I could try some factors of negative 12, like 6 and 2. I know those multiply. I need to make one of them negative, but those are not going to add up to 1. They have a difference of 4 or negative 4 or 8, so that they're not going to have the appropriate difference that we need, because that would add up to 4. So instead, let's try a different set. A negative 12. Whoa. Let's try 3. 1 and 12 I know is way too far apart. Let's try 4 and 3. I could make 4 negative and 3 positive and try that. They multiply to negative 12, but they would add up to negative 1. Oh, well, at least we're close. I'm just going to change the signs around. 4 negative 3 multiplied to negative 12, and then if I add them, they go to 1. Yep, so I've just taken that time to choose numbers that multiply to negative 12 and add to 1. Let me fill them in as my factors. X plus 4, x minus 3. So we factored that on top. On bottom, so my x factor. Again, this one here, we saw it in the something like it in the first video. You can either treat it as a difference of squares, so you know that it's going to go to x and a plus or minus the square root of 9, which is 3. Or you could again treat it as a quadratic, except it just doesn't have a middle term. So we need numbers that multiply to make -9 and add up to 0. Well, that means they have to be opposites, and the only opposites that multiply to 9 are positive 3 and negative 3. Those multiply to -9 and add to 0. So the factoring takes a little bit of time to explain, but once we're practiced with it and used to using the common things, it goes pretty easily. So now we have standard form, we have factored form, ready to continue on our process. So domain, it's a good place to start. Again, I like to use my factored form, and in particular, the denominator of the factored form. That's what we're trying to avoid dividing by 0. So I'm just going to take each of my terms and say, well, this first factor, x, cannot be equal to 0. If it was 0, the whole denominator would be 0, and we can't have that because then we'd be dividing by 0. The second one, x plus 3, cannot be equal to 0. If that factor were equal to 0, the whole denominator would be 0, and that would be a problem. And the last one, x plus 3. Oops, I did the x minus 3, x minus 3 cannot be equal to 0. Those are 3 different factors, give us 3 different values of x. First one's already solved. Check. Second one I need to solve, minus 3, x cannot be equal to -3. And the third one I need to solve, plus 3, x cannot be equal to 3. So there are 3 values that I cannot have in my domain, that are excluded from my domain. So x is anything but those 3. Then remember up here, we moved on from our domain and decide for each of those values, was it going to form a vertical asymptote or a hole? Now I'm going to go down here and look at these. Remember our reason was it makes a vertical asymptote unless we can remove it. So let's see if we can remove any of these. If I go up here to my factored form, oh yeah, I notice right away that x minus 3 is in common on top and bottom. So I could divide it out or remove it, and I would just be left with this simplified function. But okay, so that's actually useful. I can't divide anymore else. So that's useful. No, the first one, the x cannot be 0. That's going to make a vertical asymptote because I could not remove it. I couldn't divide. There's no x term in common on top to divide out, so it's going to remain a vertical asymptote. This one here, this middle term, the x plus 3 factor, I couldn't divide it out. There was no x plus 3 factor on top to divide out, so it remains. It's going to stay a vertical asymptote. X equals minus 3. But this last factor, x minus 3, I could remove it, so this value is going to form a hole at x equals 3. So it won't be an asymptote, but there will be a specific value for which our function's undefined. Cool. So we've done the domain, we've gotten the vertical asymptotes and a hole, and then we just need the x-intercepts. Again, we found that by setting our f of x, our function, and again, we like to use the factored version for this. Set our function equal to 0, and I'm actually going to use the simplified version for this because it's a little easier to work with. Again, here we really only care about the top because that's the part of our fraction that'll make it equal to 0. So I'm just setting anything on top equal to 0. 2 times x plus 4 equal to 0. I guess I could distribute the 2, or I could divide. I'm just going to divide it off since it's already factored. X plus 4 equals 0. Subtract 4. X is minus 4. So that's going to be our x-intercept. Okay, so we have some cool features to start making. Oh. 1, 2, 3, 4, 5. I'm going to go to negative 4. 1, 2, 3, 4. There's an x-intercept. Negative 3, I have a vertical asymptote. I also have one at x equals 0, which is my y-axis. And then somewhere over here, wherever our graph is, there's going to be a hole at 3. We don't know where our graph's going to be just yet, though. Alright, so I'm going to wrap this up because our video is getting a little long. For the end behavior, we care about what happens, and we use our standard form at the end. We use our standard form. The most important factors from the standard form are 2x squared over x cubed. There are 2 x's in common, so I'm going to divide out an x squared from top and bottom. It's going to leave me with 2 over just 2 over 1x. And then if I think about what happens as my x gets very large and very small, or sorry, very positive and very negative, my function is going to go toward, what do I get if I do 2 divided by a huge number? 2 divided into tiny, tiny pieces is going to get closer and closer to 0. At infinity, we're going to have 0. So that means both directions, left and right, our function's going towards 0. So that means that we have a horizontal asymptote of y equals 0. Let me go up here and graph it. I'm going to do it in light blue. Horizontal asymptote at y equals 0. So far left and right should touch that. And then our y-intercepts, I just plug in 0. 0 squared plus 2 times 0 minus 24 over 0 cubed minus 9 times. So I just plugged in 0 everywhere. I think, though, that I'm going to get undefined because, we knew that x equals 0 was already not a valid number for us to have. It's one of our discontinuities. It's an asymptote. So there are going to be no y-intercepts because x equals 0, the y-axis, is already an asymptote. Great. At this point, I think it's good to use our calculator and plug in. You could check some values if you wanted to. By looking at it, I know that it's going to come towards 0 from the positive because we were plugging in stuff over here. And there's no x-intercepts, so I know it has to be just on one side of this. Again, the bottom degree is odd, so it should change directions. Or go in opposite directions to the asymptote, so it's coming from the bottom. I could try and draw it through up to miss the next one, but I know there's no x-intercept in here, otherwise I would have found it. So it must turn around and go back down. And then, again, it goes opposite directions, and it's got to cross through there, but I know eventually toward the end it's got to head toward 0, so it kind of crosses through and comes back up. And if you check this in a calculator, you'd see that this is a pretty good estimate. All right, there are 2 more problems to practice this on in the packet, and the solutions we posted below this video on the website.